Welcome, people. It is my great pleasure to invite Dr. Elowyn Yager to give the DeFord lecture today. And she is being supported by the Dawn R. and Patricia Kidd Boyd lecturer endowment, basically. And Elowyn I've known for a while, but you did your undergrad work at SUNY Buffalo, a PhD then at UC Berkeley, working with Bill Dietrich, a postdoc at ASU with Mark Schmeckley, whose name is up there, and then since 2007 have been at the University of Idaho, not Iowa, and it's actually funny because we were literally talking about that last night, but anyway. In the Civil and Environmental Engineering Department, you're a professor and also the co-director of the Center for Eco-Hydraulics Research. So thank you for being here, and take it away.
Thank you for having me today. I'm really excited to be here. And what I am going to talk to you about today is about vegetation in river systems, and what I hope to convince you is that the influence of vegetation is often more complex than we think, even though we already think it's super complex. And I'd like to acknowledge Megan Kenworthy, whose PhD work makes up the latter part of this talk, and Andrew Tranmere, who's a research professor who led some of the work in the middle of this talk. And so, as many of you probably know, vegetation is ubiquitous on the Earth's surface and affects delta and floodplain deposition rates. And practically, vegetation is often used in river restoration projects in that it's assumed to increase bank strength, so also providing shade for rivers to lower temperatures for aquatic organisms. And it's also assumed to cause deposition in that it slows down the flow velocity, and if the flow velocity is slower, you can transport less sediment. But in recent experiments and in field observations, vegetation has been observed to cause both deposition and erosion. And so a question that everyone is asking is, what does vegetation actually do? Does it really cause deposition, as we often assume? And then there's been a lot of work on trying to understand how vegetation influences channel morphology. So these were experiments conducted by Mikkel Tal in 2009, where she ran an experiment with pink is water, brown is sediment, and then through time is going from the top to the bottom of the image. And what you'll note is that she planted some alfalfa sprouts to simulate vegetation in the second image, and the channel transitioned from a multi-thread, so multiple channels, to a single thread channel because of the vegetation. And so vegetation has been hypothesized to control channel form in that it allows channels to transition from multi-thread to single thread. And that was followed up by work by Christian Broderick, who also conducted experiments with simulated vegetation as alfalfa sprouts to show that you can have a straight channel transition to a meandering channel if you have this vegetation that provides bank stability. Also, he found that you needed a lot of fine sediment source, and I'm going to go into the importance of that fine sediment later on in the talk, but the main thing is that a lot of people have said vegetation will cause a channel to transition from multi-thread to single thread or meandering. And then, of course, in sedimentological literature, there's the hypothesis that the rise of land vegetation in the Silurian allowed channels that were formerly braided and steep to transition to meandering and alluvial sediments. And some people have said that meandering channels didn't exist before this rise of land vegetation. That's being hotly debated right now in the last 5 years or so as to whether that is true. But this is again predicated on the assumption that vegetation leads to meandering. And so what we're going to ask today, not necessarily about the Silurian, but does vegetation always promote meander stability, or can there be times when it actually promotes meander instability? Like you see in this image, this is not a meandering river, but there's tons of vegetation there. So the three questions we're going to step through. The first one is just a basic question of how does vegetation affect turbulence and sediment transport? And that's going to help us answer the next question of, does vegetation cause deposition and erosion, and why? or does it cause a mix of those, and why? And then finally, could vegetation lead to meander instability? So we focus on this first question. I'm going to briefly go through some experiments that were conducted a while ago in collaboration with Mark Schmeckley, where we're simulating vegetation through rigid cylinders. And you might look at this and say, Elowyn, this looks absolutely nothing like vegetation to me. And I would say, yes, I agree. That's not the point of these experiments. The point was to simplify it to the point where we could actually make measurements of flow and sediment transport through the simulated vegetation so that we could understand the simplest case, and then we can add complexity later, which we'll deal with real plants later on in this talk. The other problem was that we're making laser measurements and video measurements, which is really difficult with real vegetation. And so if you want an analog to this type of vegetation, it would be trees or reeds in rivers, but things that lack stems, things that don't pronate. And so in these experiments, we're transporting sand through regular cylinders, and they were scaled to have Reynolds, Froude numbers, etc., similar to what we see in natural rivers. And then in between the experiments, we varied the vegetation density by area from 0% to 4% to represent the range of possible vegetation densities you might find in a river system, where 0% is no vegetation. And we use particle imaging velocimetry to measure the flow field. And this allows us to have neutrally buoyant particles in the flow that's illuminated with a laser. Then we have a high-speed video that videos that laser, and the high-speed video allows us to calculate the mean flow velocity at all points in the laser, as well as turbulence characteristics. And there's two turbulence characteristics I'm going to talk about today. One is the turbulence intensity, which is just kind of a measure of the mean amount of turbulence that you see in the downstream direction. And another one is turbulent kinetic energy, which is the same thing, but it incorporates all three possible directions of flow. But essentially, the main thing you need to know is that the bigger those are, the more turbulence you have. And then we use the high-speed video mounted above the frame, the flume, to measure sediment transport around those cylinders. Where this is a video, hopefully you can find, it's very blurry when it's this big, but you can see some individual sand moving around those cylinders, where there's a lot of sand moving immediately adjacent to the cylinders and downstream, and there's not much happening here in this intervening area. And so the presence of this vegetation, kind of like bridge piers, is causing local scour that might otherwise not happen. And we can use those videos to then calculate a sediment transport rate, where we get the sediment transport rate as a difference between two successive images. So we just take those images and we calculate the difference between them, which is what's shown for an example in this image here, where white are things that are different. But this isn't giving you an actual rate, it's just giving you differences between images. And so to actually get a rate at every location, what we do is we sit and watch that video and count grains as they move across the video. And I've tried to outsource this to other people, but since it requires a lot of concentration of something that's extremely boring, I have found that this is something you have to do yourself. So don't outsource super boring stuff. I've learned you don't get good quality data. So once we've calibrated this, then we have measurements from the video and our little grain counts. We can then get a map of sediment transport everywhere in the flume, which is what's shown here, where the brown circles are the cylinders, and then flow is from right to left, and high transport is in red, low transport is in blue, and what you'll note is, just like you saw in the video, we have high transport immediately around those cylinders and downstream of them, low transport in the area in between them. What we really care about is comparing the effects of vegetation on that transport. So these are two different images from two different experiments. The one on the left had no vegetation. The one on the right had a vegetation density of 1.7%, but they had the exact same mean flow velocity. So mean flow velocity was held constant in these experiments. And what you'll immediately notice is there's a lot more color, the one on the left or the right, which is showing there's a lot more spatial variation in transport that's driven by that vegetation. And if you were to just eyeball this video or this image, you could definitely say, okay, this one on the right has more transport on average than the one on the left. So vegetation is inducing more transport than would otherwise occur for the same mean flow velocity. And this is problematic because when we calculate transport in rivers, we use mean flow. We use an average flow condition happening in that river. We don't include whatever is going on in this image, which is causing more transport. And I can actually give you data rather than asking you to eyeball an image, which is all the experiments that we conducted here, where we have the sediment transport rate plotted as a function of the mean flow velocity. Each different colored line is a different vegetation density, and each different symbol is a different experiment. And if you just look for the same mean flow velocity, as we increase the vegetation density, we get higher sediment transport rates, and sometimes we can have about an order of magnitude or more increase in sediment transport with vegetation. So in our experiments, vegetation was increasing sediment transport, and it increased it dramatically for the same mean flow velocity. So why did this happen? Well, it's all about turbulence. So what I'm going to do is show you two videos. The white dots are neutrally buoyant particles in the flow. The one on the left is without vegetation. The one on the right is with vegetation. And they have the same mean flow velocity. And we'll just let you watch them for a minute without saying anything. And so what you should see is the one with vegetation has a lot more fluid mixing. We have packets moving up and down in the flow. It's a lot more chaotic than the one on the left. The one on the left is still turbulent flow, but it has lower amounts of turbulence happening. And if you look closely at the bed of this video, you can see some large particles moving along the bed. And that's sand particles that are being transported by that turbulence, whereas the video on the left, there is no transport because the turbulence is lower. And so vegetation is increasing turbulence, and we can quantify that using these videos to turn these into turbulence intensities, which is, again, what we've plotted here. Instead of sediment transport, we have turbulence intensity as the mean function of the mean flow velocity. Same sort of color scheme for each different vegetation density. And we see for the same mean flow velocity, as you increase your vegetation density, you increase your turbulence, sometimes by about a factor of 2. And so what's happening is our vegetation is increasing turbulence. That increased turbulence is causing more transport. And this is not limited to these experiments that I just showed you. Since we published this paper, there have been many other studies that have backed this up, showing that vegetation can increase turbulence and can increase sediment transport. So this is somewhat counterintuitive because we often think vegetation causes deposition. So, quick summary, vegetation increases turbulence, it may increase sediment transport, but there's a lot of things that we are not accounting for in those experiments and in other people's experiments to answer the question of, does vegetation cause deposition or erosion, and why might that happen? And to think about a more complex case that's more similar to what we see in real streams, when the video I just showed you had vegetation through the whole flume length, the whole flume width, right? There's no river that actually looks like that. Vegetation does not grow across the entire river, doesn't grow down the entire river. And so what realistically happens in rivers is that vegetation grows in patches or on bars in rivers, like you see here. And this was a study that I wasn't involved in, but they did these interesting measurements where they have the velocity that they measured, so the average velocity over time is divided by the free stream velocity. And so when that ratio is 1, the velocity is equal to the free stream, which is far away from the vegetation patch. And if you look at these gray triangles, which are that velocity over the free stream, you see as the velocity is approaching the patch, it's decreasing. It decreases through that patch, and it's low in the patch wake before it increases again. They also measured The turbulent kinetic energy was just that measure of turbulence that I was discussing before, which are plotted in the open triangles, and you see low turbulence upstream of the patch, high turbulence in the patch, and then again, low turbulence downstream. And so they're seeing these two competing effects. Vegetation is decreasing velocity, but increasing turbulence. If you decrease velocity, you would expect lower transport. If you increase turbulence, you expect higher transport. So to figure out what that would do to deposition, they measured suspended sediment deposition around this patch, which are shown by the open circles, compared to a control amount of deposition in gray. And we see there's lower deposition in the patch than there is everywhere else. We have a lot of deposition downstream. So in this case, they're seeing, if we're having competing effects of velocity and turbulence, that turbulence is in a way winning out, and that we're having lower amounts of deposition than what we would otherwise expect in a patch. So vegetation is not causing deposition. In some cases, it's causing, compared to a location without vegetation, it's causing erosion. But other studies have found that vegetation causes enhanced deposition. So what's going on? Is there some universal thing we could say about vegetation? Does it cause deposition? Does it cause erosion? Or is it just a wash and we can't say anything at all? And I would say that there have been limitations, though, in a lot of these experiments, and that they've been conducted in small flumes, including my own. We're using simulated vegetation instead of real vegetation. A lot of them don't involve any bed load. They're involving only suspended load. We're using a constant flow, whereas in rivers we have hydrographs. And there's no upstream sediment coming into the flume, or there's a very low amount, whereas rivers have sediment supply. So to address a lot of those issues, we went to Andong in Korea, which has an experimental facility run by the KICT, where they have 3 huge outdoor flumes that are the scale of real rivers. For example, this one is about 200 meters long and 4.5 meters wide, and you see real vegetation growing in this flume. So we address a condition of scale. We have real vegetation. That allows us to address some of those limitations. And this is a plan view of that flume. Note we have about 70 or more meters upstream of where we planted this willow patch, or I should say they planted a willow patch. It was 2 years old when we conducted our experiments. It's shown here. And now you can imagine in a facility like this, it's really hard to feed sediment into the facility. They're taking water out of a river and just dumping it directly into this experimental channel. And so the only way we could supply sediment is taking a essentially dump truck, backing it up, and dumping this pile of sediment upstream. And then we're going to erode that pile of sediment as our supply pile. So we had 2 different experiments. One was a high supply and one was a low supply. But we wanted both of those experiments to have sufficient enough supply that we could still see deposition in theory in the vegetation patch. And so the only way we could do that was by changing the flow hydrograph. And so this is essentially a recession limb hydrograph. We ramp the flow up to the peak, and then we slowly step down the flow, where HSE is a high supply, where we spend a lot more time at high and moderate flows, and LSE is a low supply, where we spend a lot more time at moderate and low flows. And so the thought is, if we did this, we would have a difference in the amount of sediment eroded from this pile and fed to the willow patch. And we did scan the supply pile after, and we had 300% more sediment eroded in the HSE than in the LSE. So we did have a lot more sediment supplied to this area. And what I really want to highlight was that these hydrographs were run continuously for almost 2 days. You see experiment duration of over 40 hours. So this meant running hydrographs at night, outdoors. I actually wasn't there. This was good for me, I guess, in that I didn't have to do it. I just designed the hydrographs, and they said, here you go. But that meant everyone else was very unhappy with me, and they had a lot of coffee and fried Korean chicken, which I'm disappointed that I missed out on at least. So they ran these experiments continuously because we didn't want to influence what was going on. And we wanted realistic durations like you would see in a real river. Because we ran these experiments continuously and KICT doesn't have a sonar scanner, we could only measure the bed topography at the end of each experiment, which is what's shown here, which is the change in bed elevation. From the beginning of the experiment, we had a flat bed, to the end of the experiment, where the high supply is on top, the low supply is on the bottom. The free stream, where we're not influenced by that vegetation patch, is shown here. And then our study site, which includes the vegetation patch outlined in red, is shown here, and we're going to focus mostly on this study site. For those of you that like bed forms, this is not the focus of this talk, but I throw it in there. You notice just by looking at this image, we have some pretty nice bed forms upstream the free stream section, and then those bed forms were halted by the vegetation patch, which we've seen in other experiments. I just think that's interesting. The roughness is halting these bed forms from forming, or keeping them from forming or migrating. But just visually looking at this, we see red in the free stream, which means we had deposition. And so we have deposition regardless of the supply. Low supply, we had deposition. High supply, we had deposition. So that means we're not limited in our supply. If you had a really low supply, you might expect erosion in the free stream. So both of our experiments caused deposition in the free stream. But the amount of deposition and erosion, if you just look at this figure, eyeballing it, really depended on where you were relative to the patch. We're going to focus on 5 different locations. The patch itself, the main channel, which is here where most of the flow went, a side channel around the back of the patch wake, and then the head of the patch. So these are the median bed elevation changes in each of those zones, where the high supply is in red, the low supply is in green. Those dashed lines are what we're estimating to be the error of our DEM of difference from the beginning to the end of the experiment. So if our bars are within those dashed lines, we're saying we probably don't see much change within the error of our measurements. In your note, free stream section, we had deposition, as I just said, in both experiments. And we look at the study section, and in both experiments, even for high supply, we have erosion. And so what this is telling us is that around vegetation, we can actually enhance erosion within a river reach, at least in these experiments, even when we have a high amount of supply. But that amount of erosion was dictated by what's going on in each of these 5 zones. Where in 3 of the zones, we could say, generally speaking, we either had no change or we had deposition. So in the patch head, the interior, and the wake, we generally had deposition, particularly for the high supply. The low supply, sometimes we had no change. Whereas in the main channel and the side channel, we consistently had erosion. And sometimes we had massive amounts of erosion, for these experiments, and the amount of erosion generally correlated to the sediment supply. And so what I'm going to try and explain to you then is, why do we have erosion in the main channel as an example of where we have erosion, and then why do we have deposition as an example in the wake, where both of these zones had one consistent thing happen between each experiment. And when people are normally talking about deposition and erosion in vegetation, they normally think of it's caused by the flow in the vegetation, like the velocity or the turbulence. But as any geomorphologist worth their salt will tell you, deposition and erosion is driven by a sediment mass balance. It's not just driven by what's coming out of an area, which is, I think, what a lot of people forget when they're talking about vegetation. And in particular, deposition and erosion isn't driven by the mean sediment supply that we dictated in our experiments. It's dictated by that local mass balance. So here's our vegetation patch. We have an influx and an outflux into that vegetation patch. So when that local influx is greater than the local outflux, we expect erosion, or deposition, sorry. And when the local influx is less than the local outflux, we expect erosion. But both the local influx and the local outflux are going to be controlled by the flow hydraulics. And we just said we have these competing effects of vegetation decreasing mean velocity but increasing turbulence likely. So how do we include both of these when evaluating if there's deposition and erosion in a patch? And we do that by measuring the mean velocity and the turbulent kinetic energy with an ADV in various locations around this channel, not using this PIV. Then we calculate something called the critical velocity, and that critical velocity is a velocity that's needed to start sediment moving. And we don't calculate it, I should say we estimate it by using concurrent measurements of sediment transport and velocity in the free stream section far away from the patch. So we can independently come up with a velocity estimate in the free stream, but that's only incorporating the effects of velocity. What we want to do is incorporate both turbulence and velocity, and Judy Yang in 2016 came up with a way to incorporate turbulence into this critical velocity. And so she came up with a correction equation that allows you to correct that critical velocity to incorporate turbulence. And so we followed her equation then to then account for both turbulence and mean velocity. And so in this case, when the applied velocity in a given location is less than the critical, there's no sediment transport because you can't pick sediment up off the bed. And when it's higher than 1, that ratio, that means you have sediment transport. A greater value of that ratio means you have more sediment transport. So if we go back to our mass balance then, we can look at the gradient in that ratio of U to U crit. So just how is it changing in the downstream direction? So similar, if we have high influx to low outflux, we're going to have deposition. Well, that just means if U over U crit is decreasing downstream, we're going to have deposition. Whereas if U of U crit is increasing downstream, we're going to have erosion, assuming that U over U crit is representing how much sediment can be moved. So going from high sediment movement to low sediment movement means deposition. So we then can compare, to go back to our question that I've diverged on to talk about these methods, to say why was there erosion in the main channel and deposition in the wake. So let's start with the main channel. We're just going to look at both experiments combined in terms of U over U crit, because in the main channel we saw deposition in both, or erosion in both of them. And so to look at that, we're going to see the free stream U over U crit versus U over U crit measured in the main channel. Again, if U over U crit is different in them, it's going to tell us the direction of deposition and erosion. And so I've plotted those measurements here, where the main channel is in purpley blue and the free stream is in red. Again, when that ratio is greater than 1, we expect transport. When that ratio is less than 1, we expect no transport. We see that for all the discharges in which we made measurements in both of those hydrographs, U over U crit in the main channel is greater than that in the free stream. So U over U crit is increasing in the downstream direction, which means essentially we are able to move more sediment in the main channel than is being supplied to the main channel. So that means we should have erosion, which is what we measured. And so what we're saying here essentially is that we can use the combination of mean flow velocity and turbulence to explain this erosion we see in the main channel. But it's how U over U crit is changing, not just what it is in the main channel. And I don't want to overwhelm you with figures, so I'm just going to state this and hope you believe me, but I can show you them if you want. If you look at what actually happened independently to U and that turbulence, U increased from the free stream to the main channel, but turbulence decreased. And so they're not doing the same thing, as we said before. And so if we had just used turbulence, because turbulence is decreasing, if we only use turbulence to estimate if there's deposition and erosion, we would have incorrectly said there would be deposition. So the point here is that you need to use both mean velocity and turbulence in order to calculate if there's deposition and erosion. You can't just use one or the other. Similarly, we said what's going on in the patch wake where we saw consistent deposition. We compare U over U crit in the patch to U over U crit in the patch wake. Patch is in green, patch wake is in orange. We see that the patch consistently had higher U over U crit than the wake, which means U over U crit is decreasing as we're moving from the patch to the wake. decreasing U over U crit predicts deposition. And so that's what we saw in the patch. So again, these flow measurements are representing at least some of the mechanics we expect to explain why we see deposition and erosion around the patch. Also, note that there's no transport for many of these flows in the wake. So we're supplying sediment to the wake, and the sediment's just dropping out because the wake can't move it. So that's also why we had deposition. Again, interestingly, the turbulence decreased from the patch to the wake, but U was constant. So turbulence decreased, it was high in the patch, low in the wake. U didn't change. So if we only use U to predict deposition and erosion, we would have predicted no elevation change. And that's what most people are doing when they're predicting sediment transport. They're completely ignoring turbulence. And they would have said, okay, there's no deposition because my mean flow velocity is the same in the patch and in the wake. So the main point is that we need both of these flow parameters. We need some estimate of the turbulent fluctuations, and we need some estimate of the mean if we want to accurately represent deposition and erosion around vegetation. The final thing I want to talk about in these experiments is what's going on in this interior. We see deposition for the high supply and nothing really going on for the low supply. And you might think, okay, well, there's low supply, so that's why we don't have much deposition in the patch. But if you remember, going to the free stream, we had plenty of supply to cause deposition upstream. And so if we're causing deposition in the patch that's greater than the free stream for high supply, we would expect to see the same sort of thing for low supply. So we can go back to our sediment mass balance, but in this case, we actually measured bedload transport going in and out of the patch using bedload samplers. So we can directly calculate what's coming in and what's coming out to see who we expect deposition or erosion during all the different flows within the hydrograph. So we measured in and out every discharge to calculate what's going on and what's explaining that end result of some deposition during high supply and almost none during low supply. And if we just look at the low supply experiment here, we have that ratio of sediment outflux to influx. So when that ratio is greater than 1, it means erosion. When that ratio is less than 1, it means deposition. Each different symbol is a different measurement of sediment transport during the low supply hydrograph. Remembering the time in the hydrograph is moving from your right to left. So we're starting with high discharge, going to low discharge. And what you see from our mass balance is we have erosion during high flows and deposition during low flows. So even for the same experiment, even though we measured relatively tiny amounts of deposition, we're actually observing if you dig deeper into the hydrograph, you can get deposition and erosion during that same hydrograph and during that same supply. And so what this is telling us is that it's really hard to say if a patch is going to have deposition or erosion or what's going on in that patch if you just measure things that are happening after an event in a river or after maybe a flume experiment where you don't have measurements within it. And so a lot of times, maybe when we're seeing deposition in vegetation patches, that's driven possibly by lower flows that might be causing that deposition. The reason for this was because we had a consistent low supply into the patch, and then our outflux from the patch changed. So we had enough supply, during low flows, but we couldn't move that sediment, which caused deposition, and then we didn't have enough supply during the high flows, which caused erosion. Now, if we look at the high supply experiment, you might expect, because we had a lot more deposition, that would just shift this line down, right? We had more deposition during high supply experiment, so everything should just be more towards deposition. But if we look at what we actually measured, we just flipped the axes and it's a total mess. We have now deposition during high discharges and erosion during low discharges. I know, it's a lot to wrap your head around. So what's going on here? Well, there's something that's complexity in what's going on in the morphology. So we have high supply at the largest discharges. Remembering time is over here, it's starting at 6. So our largest discharges, there's tons of sediment being imported into that patch. It's allowing it to deposit sediment because it's not outfluxing that amount of sediment. But when we get to these lower discharges, we start to see erosion, and that's largely driven, if we look at what's actually coming into the patch, by no sediment coming into the patch. We have a high supply overall, but there's nothing actually coming in locally to the patch. And that's because there is a huge mound of sediment depositing upstream of the patch. And that started to deposit during the highest discharge. And the elevation of that was about 15 centimeters, which doesn't seem that large, but in the scale of this vegetation, it's pretty large. So it was forming during the high discharge. It allowed sediment to go into the patch during the high discharge, and then it kept sediment from going into the patch once it had formed at that low discharge and routed sediment into the main channel. And so in this way, there's a morphology feedback going on where even though we have a really high supply, because we have that high supply, it causes huge amount of deposition. That huge amount of deposition cuts off the sediment supply downstream, which then allows there to be erosion. So the point here is that if you just assume high supply deposition, you're likely to be wrong because these morphodynamic feedbacks are really important. So does vegetation cause deposition and erosion? We find that in a patch it really depends on the hydrograph. During a hydrograph you can see both deposition and erosion for a given supply. It depends on that reach scale sediment supply. More likely you're going to see deposition with high supply, but it might not depending on that feedback that you see around the patch with deposition of mounds either upstream or downstream. So the short answer is it's complicated and it's difficult to predict. But in a given reach, patches likely cause erosion adjacent to them. And we're not the only people who have found this, so it's not just our study. A number of studies have now said around a vegetation patch you're likely to have erosion because of that increase in velocity. So on average within a reach, a vegetation patch could actually lead to net erosion. And this is really important when we think about implications, in that river restoration projects are often using vegetation to cause deposition, increase channel stability, but vegetation might not always lead to deposition and could in fact help erode itself out. So you could spend all this money planting vegetation, it could enhance erosion, and then your vegetation could wash out. And finally, if you do want to estimate whether vegetation is going to cause deposition or erosion, you can only really do that if you account for the gradient in sediment transport, meaning how sediment transport is changing upstream to downstream, and you need to include both the effects of mean flow and turbulence. You can't just use one or the other. Finally, could vegetation lead to meander instability? And this one is going to be way quicker than that middle part of the talk. We're going to go one step down in scale to the outdoor stream lab. Maybe some of you have been there at St. Anthony Falls Lab, where essentially we have the banks of the Mississippi here. They've constructed an artificial meandering channel on those banks, taking water from the Mississippi, feeding it into this fake meander channel. We can actually supply sediment in this case because it's a reasonable scale experiment. And what we're going to do is run two different hydrographs again, recession hydrographs only, starting with a peak flow and then decreasing the flow in steps, where we have a 10% recession over here. That's representative of what we might expect for snowmelt dominated flows, and a 30% recession rate over here, which we might expect for either rainfall dominated flows or regulated flows. Now note that our peak flow for the 30% was higher, peak discharge, and that'll be important when we come back to it in a few minutes. But the sediment supply was essentially, total amount of sediment supplied between each experiment was identical, which is why we needed to have the higher peak flow. I'm not going to go into those details, but the main thing is we didn't vary sediment supply between the experiments. So sediment supply is not explaining any differences you see. Then we ran each of those two hydrographs with and without vegetation planted on a point bar. So flow is from top to bottom in this image. There's the main channel. Point bars are naturally formed in the OSL by transporting sand, in some cases a little bit of gravel. This is not the vegetation that was in the experiment. This has been cut for us to allow us to scan the bed, but the vegetation looked like this initially, where it was not cut, and we planted it in consultation with an ecologist to replicate where we expect vegetation recruitment to happen on a bar. Then we measured the topography during experiments at each of those steps of the hydrograph using a sonar scanner that's over the apex of the bar. So here's the bar here, there's the main flow. Flow is from left to right and through cross sections during each experiment at the end. What I'm just going to talk about, because we have limited time, is what happened at the end, or what you see at the end. So we're just going to look at the sonar scan at the apex. So these are the experiments without vegetation. We have the 10% recession on the left, 30% recession on the right. But you'll note we have the bar top denoted with this line. And the 30% recession ended up with a much higher bar top. And that was partly because we had a higher peak flow that could deliver sediment up higher in the channel. But it also is because we quickly dropped the flow down, which allowed that bar top to remain and not get eroded during lower flows. Whereas the 10% recession rate had a lower bar top and a less steeper face into the main flow. But the main thing I want you to notice is that if we look at the vegetation experiments, where we have vegetation planted on these bar tops, we see generally the same result between those two different recession experiments: higher bar tops with 30% recession, lower bar tops with 10%. But if we look, there are subtle differences between these two experiments. Focusing on this area here and this area here that do not happen in this 30% recession rate. If we zoom in on those areas a little bit, I note that we had vegetation planted right here where we have the high bar top, and then we have this area of low elevation around the vegetation. Similarly here, we have a much lower area of low elevation around the vegetation. And what those are is a side channel that developed because we planted the vegetation. That side channel did not exist in the other experiments, and that's because the vegetation was routing the flow around itself and increasing the velocity around the bar top. And that side channel, which you can just visually see, persisted more in the 30% recession rate than it did in the 10% recession rate. And that's because in the 30% recession rate, we dropped the flow so slowly, we were able to keep delivering fine sediment that could fill in that side channel somewhat, whereas the 30% recession rate, we dropped the flow so quickly that sediment couldn't get into that side channel and fill it in. And so to take a look at what that channel looks like, flow is from top to bottom. This is the inner bank to outer bank. Here's the side channel, partially filled in at the end of that 10% recession run. Now, the idea here is that it's possible, of course, we have this matting that's stabilizing the OSL, and they would be really mad at us if we started to cause erosion of this channel. But if we didn't have that mat stabilizing it, it could be that since we're routing sediment around the vegetation, we're going to start causing erosion around that vegetation and disconnect that point bar from the bank and lead our meandering river to eventually cause a multi-thread channel rather than a single thread channel. And this is essentially going back to what Christian Broderick found in his experiments, where he said he needed some supply of fine sediment, and he needed that supply of fine sediment to fill in chutes, essentially, that developed in the point bars. But his chutes didn't develop because of vegetation, they just developed without vegetation. He only planted vegetation on the floodplain. And so a question, essentially, that I have is, if he had vegetation planted on his point bars, would he have been able to have these stable meanders forming, or would the vegetation have led to multi-thread channels? And in case you think this is just an experiment, one experiment, if we go back to our KICT experiments, we didn't talk about this at all, but again, the side channel had erosion. And so in a straight walled flume, we also had erosion of that side channel. And so it could be possible that we would erode and expand the channel width. And if we were allowed that channel to meander, we could also cause the channel to be a multi-thread river. So could vegetation lead to meander stability? Possibly. Of course, this isn't the be-all, end-all. These are just two experiments. But the main point I'm trying to say is we often assume vegetation causes meander stability because it increases bank strength. But in this case, we see in all the previous part of this talk, vegetation can increase erosion. And depending on where the vegetation is growing, it could cause multi-thread channels. And with that, I just want to acknowledge funding from the National Science Foundation, KICT, and the National Center for Earth Surface Dynamics. Thank you.